First of all, I would like to thank you to Mr. KUABAN for the presentation and welcome our participants. Today, Mr. KUABAN will give us a speech on modeling of energy depletion process and battery depletion attacks for battery-powered IoT devices. KUABAN, could you please make a short introduction of yourself and your institute, please? Then please start to your presentation. Thank you. Thank you very much again.
Okay. My name's KUABAN Godlove KUABAN, and I work at the Institute of Theoretical and Applied Informatics of the Polish Academy of Sciences, precisely in the group of computer systems modeling and performance evaluations. And I will be presenting on the modeling of the energy depletion process and battery depletion attacks for battery-powered Internet of Things devices. As billions of Internet of Things devices are being connected to the internet, a majority of them are being powered by batteries. And in designing these systems, it is very important to take into consideration the limited energy resources, because the battery should be small, cost effective, and it should be able to supply the IoT device within a reasonable time. So in the course of designing this system, it is very important to choose the parameters like the size of the battery relative to the application that is being considered or the kind of IoT device that is being deployed. And this work gives us the analytical background on how to size IoT devices. And also, one of the aspects that we are going to be discussing in this work is the problem of energy depletion attacks, because the energy stored in the battery is very limited since we are using small batteries. It makes these devices to be vulnerable to battery depletion attacks, which are cyber attacks that are designed to induce the device to consume more energy and eventually run out of energy and can be shut down. Just imagine IoT devices deployed in an agricultural field, and then someone succeeds to conduct a battery depletion attack in these devices, maybe that are to control maybe an irrigation system, and shut them down when it is still working. You can imagine the amount of water that is going to be lost. And it happens in critical infrastructure, especially in the health, IoT devices that are for health monitoring or that are for critical application that somebody just succeeds to drain them completely and shut them down. It could lead to very big catastrophic effects, especially in those ones that are used in traffic application. So a simplified architectural model for an IoT network architecture is as shown, where we can have an IoT access network of IoT sensors connected to some access points. And in some cases, we could have a fork node that is being used to perform some lightweight computation, such that there is no need to always send the information to the cloud service, which takes a long time. And also with huge deployments of IoT with billions, tens of billions of them. Imagine the amount of traffic that is going to be flowing inside the core network. So with a fork node here, there is no need again to send the IoT traffic to the cloud. And so it saves a lot of energy that could have been used to process those packets within the core network. So this is just an overview, but our focus will be on the IoT device only, because we had the topic on saving energy due to IoT traffic in the core network is not part of this work, but we had done such a study before on trying to aggregate the IoT packets into larger ones and send across the core network, but it is not part of this discussion. So I will move to a simplified block diagram of an IoT device where you have some sensors, have some actuators, then you have a power supply module. Here in this case, it is a battery that has been charged. We assume that it is charged to full capacity and then attached to the IoT device to power all the components. And then we have the security module that is used to ensure security. Then we have the communication module for the transmission of the IoT messages. The average total power consumed by an IoT device can be given by the power that the device consumes when it is active, and then the power that the device consumes when it is asleep, where this is just a fraction of time that the device is active, and here is a fraction of time that the device is in the sleep mode, because we put the device in the sleep mode to ensure that it consumes a minimum amount of energy. From the Shannon information and communication theoretic limit, we can say that the energy needed to send a single IoT packet can be given by this formula, where PL is the path loss due to the wireless communication environment, and W is the bandwidth, and SNR is the signal to noise ratio, and N is the size of the message. If the message is larger, the energy needed to send the single IoT packet is larger, and if it is smaller, the energy needed to send a single IoT message is smaller. That is why we see that IoT messages are shorter to keep the amount of energy needed to send a single IoT message as small as possible. And PR is the receive power, while P0 is electronic power consumption overhead needed to drive the electronic components. And then eta here is a conversion factor of the power amplifier from electrical power to the radio frequency power. And so they receive power from the classical radio network model is the path loss multiplied by the transmit power, where PL is given by L0 H, where H here is a random variable which represents the fading in the channel, and L0 here is a constant that is determined by the antenna gain and the radio frequency and the propagation environment. And then D is the distance of the IoT device to the access point, and then A is the path loss exponent. Because a significant amount of energy in IoT device is used by the transmission module. Therefore, the lifetime of an IoT battery traditionally is determined by taking the battery capacity, assuming that the battery is charged to full capacity, divided by the average power that is drawn out of the battery, which in terms of which could also be given in terms of the current by the charge rating divided by the average current drawn from the battery, where here is the power drawn, here is active power, and here is the sleep mode power. So a common approach in the analysis of battery powered wireless sensor devices is to discretize the energy into energy packets, where an energy packet is the minimum amount of energy required to transmit a single data packet. This concept of energy packet was developed by Professor Errol Geldenberg, and he has written a lot of papers on it. We just use it to create an intuition in this context, in the methodology that we are using. And since energy is a continuous quantity, the changes in the amount of energy in the battery could also be considered in an analogous way to changes of a fluid in the reservoir. And considering this kind of intuition makes it possible to use fluid flow models to analyze the changes of energy in the battery. And a lot of papers have been published on fluid flow models for IoT batteries or for energy storage systems in general. And recently, diffusion approximation have been proposed by some authors. And in 2016, Professor Errol also wrote a paper on the use of diffusion approximation to model energy storage systems, battery to be precise. And we also applied it in some aspect of modeling the battery of a drone recently in a paper that we just, that was presented in a conference. Energy depletion attacks in IoT networks are attacks that are designed with the aim of exhausting the energy stored in the battery of an IoT. And the energy depletion attacks are designed to increase the energy consumption of the device, which rapidly decrease the energy stored in the battery and eventually shut down the device. Some energy depletion attacks are designed to reduce the sleeping time, because when the device is in the sleep mode, it consumes minimum amount of energy. So to cause the device to consume more energy is to sometimes cause it to wake up frequently and deprive it from the sleep time. So it consumes more energy than when it was able to follow the configured sleep time that was configured when the device was deployed. And sometimes to adjust the network parameters like the duty cycle, the data rate, the rate at which the device is sending data, and then the packet size. If the packet size is increased, we know that the amount of energy consumed by the device is going to increase. And also to induce the device to repeatedly transmit very useless packets. Some attempts have been made to model the impact of energy depletion attacks on the performance and safety of battery-powered IoT devices. And that work was based on Markovian models, which have one drawback, because they assume that the energy drawn from the battery follows an exponential distribution, because they assume that the energy drawn from the battery varies and that the variation is stochastic in nature and is exponentially distributed, which in reality is not the case, because IoT devices have a different, the energy consumption of IoT devices does not vary according to an exponential distribution in reality. And so we are proposing the use of diffusion approximation, which gives us that ability to use real energy distributions. So like if we are able to measure and get the average energy that the IoT device is can consume within a given time frame, we can be able to predict to some degree of accuracy the lifetime of the IoT device, or to predict what amount of energy would be at the battery at a given time instant. Therefore, to explain the intuition behind this method, the first assumption is that the battery is charged to its full capacity initially. And then we say that if it is charged to its full capacity B, and we are able to measure the cumulative amount of energy drawn from the battery, and let us suppose that the cumulative amount of energy drawn from the battery is ED. Therefore, at time T, the amount of energy left in the battery can be determined by subtracting the cumulative amount of energy that has been consumed from the initial amount of energy that was present in the battery. And therefore, in this kind of argument, the changes in the amount of energy within a given time frame delta would be given by because since the capacity is not changing, we assume here that the capacity is not changing, which of course we know that it is possible that the capacity of the battery changes over time. But we assume here that the capacity of the battery is fixed within a given, within the lifetime of the IoT device. And therefore, the changes in the energy depends largely on the changes in the energy consumption. And therefore, if we assume that the energy is drawn from the battery, and the changes in the energy content of the battery are normally distributed, then we can approximate the discharging process of the battery by a diffusion or Brownian motion process, which is because if we suppose that the changes of the energy is just like a diffusion process, like tiny Brownian motion particles which are moving, because the change in the position of these particles is always random. And for large amounts of changes, we can use the classical diffusion process to study the changes of the energy of the battery, and that the mean of these changes, the average or the mean of these changes is beta, and that the variance, because the changes, we are talking of the mean changes, and the variation of the changes are given by beta and alpha. So in this case, we represent the discharging process by a diffusion approximation, by a diffusion process that starts at 0 with the battery charged to its full capacity, and the process ends at time T when the energy in the battery is completely drained. So X of T is 0. And the diffusion process is described by this second order partial differential equation, which is subject, which if we solve this equation, equation 10, with the following boundary conditions, that at time T equals 0, we have B amounts of energy in the battery, given that we are starting with an initial amount of energy, B, in the battery. Therefore, initially, this is the this condition gives us the initial condition that we are starting with B amount of energy, because here is just like a Dirac function which gives us the energy at time t equals 0, because the probability that we have B amount of energy at time t equals 0 is 1. So its density is delta B, which is the Dirac function at that point. Then this is the condition that at time t we have 0 amount of energy in the battery, given that we started with B amount of energy in the battery. So, and its density is 0. So these are the conditions that we are using to solve this equation, to have the time evolution of the battery, of the amount of energy in the battery at time t. And the solution is given by this distribution. And so this gives us the distribution of that at time t, we have X amount of energy in the battery, given that we started with B amount of energy, which is the initial energy in the battery, which is the battery, like the capacity rating of the battery. And to test if this function really is the solution of our equation, we can check all the conditions by putting it back to the differential equation. It will satisfy very well. And if we check the limit as t is turning to 0, we will have delta B. And if we take the limit as t turns to infinity, so which means that as t turns to infinity, it turns to 0. Sorry, yeah, the limit turns to 0. So the battery eventually, the energies, this means that the energy stored in the battery will eventually becomes 0 at a finite time. So here gives the distribution of the amount of energy stored in the battery. If we like observe it within this type, here is the time axis, and here is the x-axis of the amount of energy present in the battery, and here is the axis of the distribution, that we have X amount of energy in the battery at time t, given that we start with B amount of energy in the battery. And if we look at it from an extended time, we see that as time goes by, the amount of energy in the battery decreases. Oh, sorry. We see that the amount of energy present in the battery decreases with time. So they're the same here, like the amount of energy decreases, because if we start here with at B, because B is 100 in our case here, we see that we have the density is very high here, and it drops with time. So here is the time axis, and then here is the energy axis. So this is the time evolution of the amount of energy present in the battery at time t. So one of the things that we are interested also is how long will the device stay alive, because we know that if the energy stored in the battery gets exhausted, the device is going to be shut down. So we consider that as the lifetime of the IoT device. And the estimation of the lifetime of the IoT device, we take the first passage time of the diffusion process from X equals B, that we have X amount of energy in the battery at time t equals 0, to time t when the energy present in the battery becomes 0. So we take the first passage time, the time from B amount of energy in the battery to X equals 0 amount of energy in the battery when the battery is completely drained. And that first passage time can be obtained by taking this this limit, and it gives us this distribution with mean given by this and variation given by this. And so if we look at the distribution of the lifetime of the IoT device for different sleep time, because we are looking at the influence of the sleep sleep time, because here if we increase the proportion of time that the device spent in the sleep mode, we see that we increase the lifetime of the IoT device, because the lifetime of the IoT device increases when we keep the device in the sleep mode as much as possible. And in case of attacks that causes the device to become awake, most of the time we see that the lifetime of the device is greatly impacted, because it becomes very small if we reduce the sleep time of the IoT device, maybe due to some energy depletion attacks that are aimed at keeping the device awake. So another thing is the active power, because sometimes there are some group of battery depletion attacks that are very hard to detect, because they tend to increase the quality of service while they deplete the energy of the battery very fast. Take, for example, an attacker jams the radio signal of the IoT device, and the device is configured to increase its transmission power to improve the signal quality. The fact that the signal quality is good gives an impression of good quality, but it is at the cost of the battery. And in one paper I saw where the authors were giving a scenario where a malware is installed in the IoT device, and it triggers the IoT device to perform some unpredictable behaviors, and sometimes even trigger the IoT device to increase the transmission power. In that case, we suppose here that if we are increasing the active power, which could be by increasing the transmission power or some other, or causing it to do some other activities. So if the active power increases, what happens is that the lifetime of the IoT device reduces. So here is the impact of increasing the active power on the lifetime of the IoT device. So equally, here is a coefficient of variation of the energy consumed by the IoT device, because an IoT device, the energy consumed the variation could be very small, which means that in normal circumstances there shouldn't be much variation, or there should be very negligible changes in the amount of energy drawn by the IoT device, because it's doing repetitive activity, which is a regular activity. So if there is some variation in the energy consumed by the IoT device, it is an indication that it is doing something unusual, and it could be due to an attack, like some random attacks happening and causing the energy drawn by the energy consumed by the IoT device to vary. In that case, that could be a solution to detecting energy depletion attacks instead of monitoring the quality of service, because most attack detectors monitor quality of service. And energy depletion attacks, one way to identify them could be to monitor the energy consumption patterns and be able to use that as a matrix in the attack detection systems. So here is the average amount of is the average lifetime of the IoT device with the battery capacity. It's a linear relationship because when you increase the battery capacity and you charge it to full keeping your device, the expected lifetime of the device. It will be depleted. We look at the influence of the proportion of time that the device spent in the sleep mode on the probability distribution of the lifetime. And we see that as we increase, it increases the probability of keeping the device alive for a longer time. When we look at the influence of the battery capacity on the distribution of the lifetime, when you are increasing the battery capacity, you increase the probability that the device is going to stay alive longer. One of the things that we considered was, in the case that you are deploying an IoT device, it could be interesting and important to know, to predict the time after which you should change the battery, because you should not wait until you are taken by surprise and the device get shut down, because in designing you should be able to say that, okay, when the energy present in the battery reaches a given percentage of its capacity, maybe when it is 30% of the capacity or 20% of the capacity, you should change the battery. This, in practice, you could configure on the IoT device to monitor the battery directly, but in the time of design, you could try to have an estimate, because you want to choose a capacity, you want to choose the fraction of the capacity after which you want to choose the fraction of the capacity after which you should change the battery of the IoT device, and therefore we get the density of such of that time after which the energy present in the battery must have dropped to a given percentage of the capacity. And so here is the density of the lifetime for different percentages. We are saying here that the probability density function, that after time psi or time t, the amount of energy present in the battery is eta b, which means that the battery must have dropped to 1 minus eta multiplied by b percent of the battery capacity. And therefore we say here that after this time, the battery must have lost 70% of the energy must have been drawn from the battery. And when we look at the impact of that percentage, we see that it greatly impacts the density of the lifetime, because here at 90%, we see that the time after which 90% of the energy stored in the battery must have been consumed present in the battery to drop to 10% of its initial capacity. That time increases, but if we say that the time after which to 70% of its initial capacity, so the time to is quick. So we look at the distribution of that time, and we look at the probability distribution of that time. So therefore, by manipulating some IoT device parameters such as sleep time and awake time, transmit power, data rate, and packet size, the energy stored in the battery could be rapidly depleted. It's because sometimes an operator deploys an IoT device expecting the device to stay gets drained so quickly. Maybe due to, but it's very important to have a mathematical framework to do an analysis when sizing and choosing some of the parameters to deploy the IoT device. And in our next work, which is currently work in progress, we are upgrading this same model by modifying the diffusion process to study the problem of sizing the battery capacity of a green base station site for a mobile network, where the base station site is supplied by renewable energy, which could be wind, it could be solar, or it could be hydro, like this pumped hydro of pumping water into a tank and discharging the water, storing the water in pumped hydro. And in this case, we have a battery management system that have a charge controller for the charging and the discharge, and then we have the core communication, data acquisition, and management system, and then the battery management system to look at the state of health of the battery or the state of charge of the battery and some other factors. And then we have a backup generator to make sure that most often in some practical implementation of green base station site, if the renewable energy source is stable enough, which means that we have enough sun or enough wind, and it is very much stable, we can supply the base station site directly without passing through the battery. We can supply it directly and at the same time storing a fraction of energy in the battery. But if the renewable energy sources are not that stable, it will be good to pass it through the battery to stabilize, to avoid the fluctuations that could affect the supply of energy to the base station, so that it passes through the battery, and then the battery smoothens the output of the energy supplied to the base station. We will consider both approaches in this next step of considering that we are using the renewable energy to supply the BTS through a battery, and also the possibility of that we are charging the battery at the same time and supplying the base station at the same time. Thank you very much. I will not go to the details of what we are doing now, but it is just the next steps of what we are doing at the moment. Thank you very much.
We thank you, Godlove. It was very nice presentation and interesting topic, actually. The security of IoT network is very important, as you mentioned. My question is there some attack detector to detect energy depletion of the devices in IoT network? Actually, your presentation is not about the attack detector, but it is my interest. What are the main features of the devices which are under attack, energy depletion attack? How can we detect, and also how to mitigate with these kind of attacks? Can you say something on it?
Yes. Attack detectors for energy depletion attacks, a lot of work has been done on. Some works have tried to address that. And one of the feature of energy depletion attacks is monitor the energy consumption. For example, if you have a benchmark of the energy consumption of your IoT device in the normal mode, then it means that if you start, it means that you can consumption of the IoT devices. And if there are some variation or some deviations, it could be a suspicious attempt that the network is suffering from some intruder that is targeting the energy resources of the IoT devices. There are a couple of works that have
okay, and
that have addressed that.
Your work on modeling energy depletion say something on it. That is what you say.
Yes.
If we model it, then we can capture some features on such kind of attack. My second question, thank you for this, for your response. Second question is on monitoring energy depletion of devices. These will be implemented on the or in a center in the network. How do we monitor them?
Okay. In this case, the monitoring is done in this way that you do a continuous measurement within some given, within some defined time interval. It must not be too close. It could be after maybe this amount of hours, you do a sample measurement of the energy consumption of the IoT device, and then you report to the access point or to maybe the best place to deploy the attack detector could be at the fork node. Like the device simply measure and then send the measured energy to the fork node, that in which the energy depletion in which the attack the detector that maybe employs quality of service, energy consumption, and some other parameters is running, and then it does maybe it is running some sort of lightweight algorithm to really figure out if this is an attack or not. So
thank you very much. Thank you very much. I understand. Thank you.
Any more question?
And one more thing, maybe Mertz can be able to help us in this area because he has a very good experience on attack detection because he has worked and published a lot on it. So maybe he can be able to help us if my response is not clear.
Right. Okay. Thanks. Okay. More questions?
Yeah, I have no question, but I have one thing, one comment actually, if you can
Okay.
hear me correctly. I think your work is very interesting, Godlove, and it can go beyond only not individual IoT devices or the IoT attack detection, but it can also be very useful in such complex systems like a smart grid or smart home environment to model the battery and as well as the green energy sources like the photovoltaic sources. And if I'm wrong, correct me. I think it will be very useful for such areas as well. And maybe we can also privately talk about it and can collaborate also with Cüneyt Güzeliş also because we have such works on smart home energy systems as well. What do you think about it? And
Yes, it is a good suggestion, Mertz, so we can have discussion on it.